Okay, good afternoon to our respected speaker here today, Chris Madsen. He's from USA. He will deliver his lecture today in this 5 days FDP program on recent trends in microwave and millimeter wave communication. So we'll start his session with a brief introduction of him. So Chris Madsen received BSc in Electrical Engineering with special honors from University of Colorado in 2016 and MSc in Electrical Engineering from Stanford University in 2019. He joined Keysight Technologies in 2016 as a product engineer with a focus on failure analysis and quality control, and is currently working as an R&D engineer with an emphasis on passive microwave and millimeter wave device development since 2019. As a senior member of IEEE in the US and a member of Institution of Engineering and Technology in the UK. So this is a very short bio of Mr. Madsen. So with this short bio, I request you, sir, to kindly proceed with your session.
Absolutely, thank you. See if I can't get this pulled up here. New hardware and new software today. This is a recipe for disaster. There we are. Can everybody see that okay? Can you see that right now? You're on mute.
Yeah. You can go ahead.
Okay, perfect. Just making sure. Okay, so good afternoon, everybody. I wanted to give you a presentation on passive device design and advancements, and this is more from a industry standpoint. I didn't get a chance to look at the speakers that you guys had prior to this. I don't know if they're primarily academic. They could probably give you better insight into the current state of the art with things. But industry, typically we run a little bit slower behind everybody, but still we're working on giving our own innovation, I suppose. I'm just going to give a little bit of background about myself and about Keysight Technologies, which is the company that I work for. Do a quick review of passive devices and filters, just for those who maybe have been away from passive devices for a little while. I know I couldn't explain to anybody what a low noise amplifier is anymore. It's been a long time. Roles and applications of filters in our design process, and then I want to step into advancements. Which is going to be with design, simulation, architectures, and manufacturing as well. And then kind of a look to the future to see essentially where we need to go industry-wise toward where the market's heading toward and what we need to do to start accommodating that. So I think we pretty much covered all of this. Actually, he read all of it off, so that's perfect. At present, I am an R&D engineer with Keysight Technologies, where I'm primarily in the realm of passive microwave, millimeter wave design and development work. Prior to that, product engineer doing failure analysis, quality control, and process improvement. So Keysight Technologies, I think most everybody in the RF world has probably either used their equipment at some point in time or is familiar with them. We're market leader in test equipment, basically, and we stretch beyond that, doing software and full solutions. But for the most part, everybody knows this is a test equipment company. We began with Hewlett-Packard back in the, oh goodness, I can't remember actually when the test and measurement division came around, but HP's been around since the 1930s. Their test equipment division broke off into Agilent Technologies, and then eventually Keysight Technologies came out of Agilent. Hewlett-Packard, Agilent are both still around, with one focusing more on, computers, printers, enterprise type stuff. Agilent's more moved toward healthcare, and then we've taken over a lot of the test and measurement work. Colorado Springs, we are in the market of thick film, ASIC packages, multi-chip modules, probes, and accessories. We build quite a bit, actually. More recently, I would say probably since 2017, we've been stepping more into the R&D realm with things, creating novel components, innovation, integration, working toward a lot of growth and evolution of manufacturing ability as well. We perform as consultants for a lot of our customers. They'll come to us with various specifications on devices that they'll need. We work with creating a design if they need to do so, assisting them with any modeling, simulation work, and then eventually producing a layout and doing manufacturing of the component if they decide to move forward with it, which is very often the case. We're still in the mode of failure analysis and quality assurance. Of course, that's always important for us. And then manufacturing, we do a significant amount of manufacturing. And that's where a lot of the R&D work comes in, is not necessarily just with design, but working on manufacturing processes as well to try to integrate newer technology into current processes without a large need for capital expense investments on things. So my particular role is all pretty much entirely customer driven, and that's actually where most of our research and development work goes into. So very often our customers will come to us with specifications that very often will break the laws of physics. At least initially we believe that when we get started. But eventually we'll make an effort to develop a means to actually accommodate those specifications and see if we can't get a device produced, manufactured off of that. The vast majority of my work, and the reason I have this bolded here, is RF filters. We do a handful of splitters, diplexers, other passive devices as well. The vast majority, I would say probably about 95% of it, is thick film, with the remainder being thin film. And there's a handful where we've got various passive components that are mounted onto the boards. But even then, they're usually associated with thick film as well. Software solutions, as I covered already, prediction, design, test, analysis, a lot of that's going to center around those customer products. Okay, so just a quick overview. If everybody's familiar with passive devices, filters, please just feel free to ignore this. Go get a cup of tea, but if anybody else needs this, it is available to you. So just as a quick overview, passive components don't generate energy. There is no active mechanism to this. Passive devices require no external power support. There is absolutely no biasing requirement. And examples of this would include, filters, circulators, splitters, duplexers, all these various devices that can be implemented either in planar form through thick and thin film, or very often with waveguides as well. All of these components are going to have some form of reactive parasitics and dissipative characteristics, and many of these will become more important at high frequency. So the basic concept behind a filter, we're generating these by cascading these reactive components very often into something similar to this, like a lumped element model. So as we know, resistor, inductor, capacitor creates a dissipative resonant circuit. As we cascade these together, we're then generating poles at these specific frequencies to ultimately create that full filter response that we're looking for. Another thing to note, being passive devices, the gain will always be less than 1. I have had a handful of devices where the gain was more than 1. Usually it's a calibration issue. So most common filter types, again, everybody probably is probably familiar with these. The two most common that we're generally asked to generate are the low pass and the high pass filters. Well, actually, I take that back. Low pass and band pass filters. The high pass, I would say, probably make up sub 10%. I have never personally done a notch filter. Nobody's asked for one, but I mean, we are ready to produce them if need be. Going back and kind of looking at this from an academic standpoint, as a lot of people will know, conversions between these filters are going to be possible by generating your low pass prototype and then moving over in between each filter as needed. So that pole location is going to be based on your filter requirements. So part of the customer specifications is generally going to be #1 roll off, which is that slope coming off the filter here. The second part of it is going to be passband ripple, which is usually going to be another big one for us. Based alone on those specifications, generally we can choose between doing a Chebyshev or a Butterworth architecture, and there are far more than that used for things like equalizing group delay. But for the most part, I would say the vast majority of our filters are using either that Chebyshev or Butterworth topology and set of mathematical governance, I guess would be the best way to put that. Once we generate those lumped element models, if we generate those lumped element models, can then be converted over to transmission lines. Most of our devices are going to be microstrip based. We don't do a lot of strip line. A lot of that is usually present in the PCBs. We do some work with planar waveguides, which still unfortunately utilize a lot of microstrip and coplanar waveguide topologies that still need to be modeled. So we're still looking for a lot of the parasitics, the inductance capacitance that's generated, especially more at high frequency, where you see that massive change in impedance. And there's also more losses associated with a lot of that as well. So even though we may be developing planar waveguide technology, we're still having to integrate a lot of those lossy components into that waveguide architecture without using some more advanced transition means to get into the waveguide. And these are just a handful of implementations. A lot of these you may have seen, a lot of them you may not have. These are very common topologies. Up here, we have got a stepped impedance topology. On the top left, I'm not sure if you can see the pin or not. Below that is the stub. Both of these are the two most common ones used for the low pass filters. And then over here on the bandpass side, you've got your hairpin designs, edge coupled, and interdigitated here. Over on the right, this is a substrate integrated waveguide, and I'll get into a little bit more detail with that. I believe the technology's been around, I want to say, since the early to mid 1990s, but it's been on a very quick course in terms of evolution. And even now, you look at a lot of papers from IEEE, IET, and a lot of that is SIW based, substrate integrated waveguide, SIW. So they're constantly making new architectures with these. They're starting to do multi-layer stack-ups with these new transitions. So there is a lot of work going into this, and there's a lot of benefit to them. There are some disadvantages, but especially as you start getting into the millimeter wave range, they really start to show their benefits more than their disadvantages. But just the basic idea behind these is your waveguide is formed just by this portion right here. And I apologize, this pen is hard to use. So just like a rectangular waveguide, you've got your A wall dimension and you've got your B wall dimension, and this forms the actual waveguide here, whereas the walls are going to be formed by this wall of vias. And you can imagine using a set of discrete vias like they have here, you're going to end up with some level of leakage in between these, which of course is going to worsen at high frequency. And as you start pushing the frequency more and more, especially beyond millimeter wave, when you start getting into things like W band, this gap does start to become more critical. And your via spacing and diameter, might go from something like this down to something like this, where you've even possibly got extra shielding in order to accommodate that high frequency and eliminate some of that leakage. You've also got a ground plane, which you can almost kind of see down here on the bottom, and then your top conductor plane, which overlays the entire substrate. So in effect, these sandwiching conductive planes form those top and bottom walls of your waveguide. So of course, filters are going to find application in a number of critical areas. One of our biggest areas is going to be harmonic rejection from amplifiers and image rejection. And not very often, but on occasion, we'll get requests for devices for delay, for phase shifting, for going from single-ended to differential balance, as an example. Not really a filter, but definitely fits into planar technology. So a great example is a super heterodyne receiver, which are found in FM radios. I did have to look it up. The frequency over in India for the FM radio band is the same as it is here, which is easier for demonstration, I suppose. But the basic idea is you have your FM spectrum that's going to come in from your antenna, The next step, this goes into an RF bandpass filter, and this bandpass filter is going to have a very rough, relatively wide bandwidth on it that is going to pull out a portion of that RF spectrum for further reduction. Once that's done, we'll get that portion of the RF spectrum there, which is then going to be fed into a mixer with a local oscillator that's going to convert that RF down to an intermediate frequency. From there, we run it into another filter, the intermediate frequency filter, the IF filter, which is then going to be a much more narrow bandwidth on here. And it's going to pull out just a portion of that so that we've got just that, which then we can push over into demodulation. So our current design process, it does change in complexity. So this is a very rough flow chart, but I'll kind of note some points where we're essentially skipping a lot of areas now, especially with, we have, what we refer to as cookie cutter designs. A customer might come to us and say, I need a very basic 12 gigahertz low pass filter. That's something we can complete very quickly. We've got templates that are set up for something like that, and they're relatively easy. So the first thing we'll get are those customer specifications where they'll tell us that, they want a specific roll-off, they want a specific passband ripple, they want a specific amount of rejection in the stop band, they may want some level of harmonic rejection beyond that initial harmonic of the filter, which is it's another fun area. But yeah, as we start working with the more novel designs such as the SIWs, then we'll start getting more into the depth of design, but always that first step is going to be customer specifications. Moving on, when we're doing initial prototypes, and I mean, this is from absolute bare scratch, we will do a lumped element model, but I would say it's relatively rare anymore for us to have to do that. If we are generating an entirely new topology, say we have an SIW, and we've determined maybe a new filtering method for this or a new means of getting a transmission line into it, that might be something that we utilize a lumped element model. Number one, to generate a rough idea of operation, but number two, to make simulation and development quite a bit easier. But I would say it's relatively rare anymore. From there, we'll get into a microstrip equivalent, and typically this will be the very first jumping off point for any relatively new filter. So we'll skip this pretty much entirely. We'll develop a microstrip equivalent, which is, again, typically done either through ADS or Genesis, which are both Keysight software. And then once that's completed, then we'll move on to the most time-consuming part of it, which is going to be the computational electromagnetic modeling. And typically we'll do that, I would say most of the time in EM Pro, which is another piece of Keysight software, but we also use ANSYS's HFSS as well as Keysight's ADS. Just depending on application. HFSS is more suited for some things. EM Pro can be a little bit more simplified than HFSS is, which does have its own benefits. And a lot of our internal models are going to be developed for EM Pro as opposed to the former. So a big part of this is trying to maintain an idea of design and manufacturing guidelines as you're doing the EM modeling. So we have requirements for line thickness, for gap width, conductor thickness, very specific substrate permittivities that we're using, substrate thicknesses, manufacturing tolerances around all of these things, via spacing between via and the edge of the substrate, the via and the conductor. So there are a lot of things that go into that as we're performing that modeling to make sure that we are not creating something on the computer that we cannot actually manufacture, which I do a lot. So. And again, this is very often the case, especially with the cookie cutter devices, is that we will move directly from customer specifications over to an EM model template and just go from there. And that's with our most base level devices that are being requested from our customers. From there, we get into prototyping and process development, and then manufacturing, test, and ship. The prototyping process, this very often occurs with any very highly novel devices that we're coming up with. Process development is just a natural part of developing higher frequency devices where you've got to find a way to decrease your via diameter on the substrate. You need to find a way to decrease the substrate thickness, for example, get your via pitch more tightly together, develop a tighter line width, develop tighter gaps, especially for relatively high bandwidth devices where that gap width starts to really come in, especially on like interdigitated filters, and that becomes problematic. And then manufacturing, test, and ship, which is, of course, the end result for anything. So now the fun part. So the average device frequency on our end has increased 115% in the last 7 years. So right around the 2015 timeframe, we were still below millimeter wave for the vast majority of our devices. And now, as of last year, 2022, we've started stepping up significantly so that our average frequency has hit the millimeter wave threshold. And that's the median frequency, I should say, not the average. So yeah, roughly about 50% of our work now is well above the millimeter wave threshold. And of course, as we know, that increase has got its share of problems associated with it. We're looking at smaller footprints, which is usually a big specification from our customers. They may ask us for a 5 gigahertz low pass filter, but hey, I need you to put this on a 2 millimeter square substrate. And it obviously there's going to be some challenges associated with that, because if you try to put a normal stepped impedance 5 gigahertz filter down onto a substrate, it may exceed, trying to think of the exact dimensions because we're still using imperial units with a lot of our stuff, unfortunately. But it could very well exceed roughly about an inch. And again, manufacturing tolerance is going to be another big one. So we're needing pretty much finer tolerances on absolutely everything. Everything is going to get smaller due to that scale and wavelength. Device losses are going to increase, and this is especially problematic with thick film, where thin film uses typically a very highly polished substrate, which is usually some form of alumina, either what the manufacturer just calls alumina, sapphire, fused silica, which is another big one. They're relatively smooth. And that's due to the photolithographic process that thin film uses as opposed to the screen printing process that thick film uses. The pastes for thick film need a relatively rough substrate layer in order to adhere properly, which unfortunately introduces excess surface roughness losses, which becomes really problematic as you start stepping up into that millimeter wave realm above 30 gigahertz. And there is some level of higher computational electromagnetic time. And this is kind of a tough area. Increased frequency does not necessarily mean higher simulation times, but it typically does mean a higher mesh density, which leads to higher simulation time. And then, of course, device complexity is going to increase. Those pitches, those line widths, everything else are going to become a little bit smaller. Coupling is going to increase. The number of elements is going to increase, and all of those things are going to tie in partially to that simulation complexity and the amount of time that it takes to complete those. So as I said, most of our devices are going to entirely skip that manual prototyping phase. And the reason for that is, as I showed you with some of those topologies a few slides back, they're fairly cookie cutter. Everybody knows how to design those, and anymore, the software is pretty much doing it for you. So what I'm showing here on the left is Genesis, which is just one piece of software that's available to develop those filters and other microwave components as well, passive components. And what this will actually do is it provides you with the lumped element model, provides you for a microstrip model, if that's the particular production process that you're actually going to be using, and it performs full optimization of that lumped element model for you, and then we'll export the EM parameters to wherever you need them. I'm not an expert on software by any means. My understanding is that Genesis is actually doing EM modeling now, but I've never used it for that purpose. So that's not to say that it can't do it, but typically what we'll do is we'll export out of Genesis into a more, I suppose, comfortable EM modeling setup. And as I said, computation time and memory utilization have decreased in some senses. And that's primarily due to some algorithm optimization. We see very often new solution algorithms that come out when software is updated. And of course, our advances in CPU and GPU architectures that have come out especially over the last 10 to 20 years, especially with regard to cloud computing with parallel computing that's available now with the GPUs. Has been available for some time, but it's now gotten to an evolutionary state where it's becoming a lot more common, I guess is the best way to put it. But as I said, that complexity and the frequency are going to play a role in the simulation times. Up here, I don't know how well you can actually see this pictured here, but I'm just showing a very rough mesh of just a very basic microstrip up top here. And adaptive meshing, which has been around for decades, you can see what's happening is that mesh density is going to get quite a bit tighter right around the conductor, which is to be expected. And then it's going to become a lot more sparse as you get out to the edge. But what's going to happen is where you have even that relatively high density mesh up near that microstrip, it's going to get even worse as the frequency increases and you maintain everything else the same, which is very often the case. You're not typically going to pull your mesh density down as you're increasing frequency to help compensate for that. So I ran a quick test, maintained everything absolutely identical, and just meshed a single frequency going down from, I think, 1 gigahertz up to roughly about 80. And then examine the simulation times. And you can see it's in a very rough exponential shape. I wouldn't fit a trend line to this because I think it's very rough. And you can see there's a lot of variation, which is kind of an oddity with that. So as I stated, GPU advancements have been a big one, especially for the finite difference time domain simulations. For the most part, we use the finite element method, but the finite difference time domain does come in use for some things, especially for quick prototyping. And a lot of that is primarily due to the fact that I'm able to utilize a GPU for that. Memory and CPU, the cost of memory and CPU performance is on a continual decrease. And this plot over here on the right side shows a lot of that. And this is, I mean, something we're all very familiar with. But since about the 1950s up to, and this is actually a projection out to 2023, it's a little bit older, but it's a nice linear decrease all the way down. And that has helped to offset a lot of the issues that we're having with going up higher in frequency and seeing that increase in device complexity. We have the computational resources to be able to kind of keep up with it, I suppose is probably the best way to put that. And then, of course, our cloud-based services, they're becoming a lot more available to us, which is a huge boon. I've had some devices, I state here that some of our stuff has gotten into the sub-terabyte territory for RAM requirements. And these are usually very complex stack-ups. Maybe we are simulating a PCB model with one of our devices. That's become a lot more frequent of a request. The customer will come to us and they will say, okay, you know, I want device X to do this particular application, but I need to know what it's going to look like when I have it mounted to the coplanar waveguide on my PCB. You know, can we put in any compensatory structures to help to offset those launches on the PCB? Can we get a good impedance match? Is it going to cause any issues with anything coupled next to it? Radiated fields, near and far fields, both coming off of the device, is that going to cause any potential issues? And I miss the days of, you know, the kilohertz RF realm where you didn't very often have to worry about these things. But again, as you start coming up at frequency, a lot of these things become issues as you start looking more into shielding and high degrees of radiation coming out of the devices. So the device design, a lot of the basic principles are the same. They've been the same for decades. One of the big advances, though, has been software. So as I stated, Genesis, and I'm not here to sell anything. I keep bringing this up because I use it very often. But Genesis is good to quickly lay out those very default microstrip strip line filters. But the issue is, for the substrate integrated waveguide, when I first started building these some years ago, I could not find any commercial software to actually lay out a very basic design. So what I did was exactly what you see on the left. Went into Python and I developed my own design software to be able to get a nice, quick, very basic prototype of the SIW that I can then pull into modeling. So that's one of the big things is if you cannot find commercial software, outside of very complex modeling, very often you can just go and create it. And that's something that I tell students here because I'll very often get the question, how important is it to actually learn programming? And I, you know, basically pull them aside and tell them, this is probably one of the most important things that you can get. Your undergraduate engineering program might provide you with some of the foundations, maybe in C, C++, or Python. But it's at a very basic level. Going on beyond that into industry or academia, it's very important to have a lot of that software background, not just to create your own software packages, but to be able to perform modeling, very quick calculations of complex systems. A lot easier than it used to be in the Notepad days, and that's initially how we were designing these SIWs, was with a Notepad and a calculator. So there is a high degree of improvement in that regard. One of the things we'll do again with those cookie cutter designs is we'll actually create templates in our electromagnetic modeling programs, and that simplifies the entire process of CAD modeling. The main thing there, as anybody who's done the simulation work knows, is the parameterization. Nothing that you pull out of any form of software that comes as an initial model that has not been simulated electromagnetically is not going to work. You will get a very rough response that hopefully will be somewhere near the frequency that you're looking for, but very often there's going to be a high degree of optimization effort that's associated with that. For the most part, a lot of that has become automated. EM Pro, for example, will tie back into ADS, and you can actually take those EM models that you've developed in EM Pro, bring them over into ADS, and run a lot of those optimization algorithms on them. And there's been a lot of advancements with those black box, computationally expensive optimization algorithms. That's the formal term for it. Just beyond the simulated annealing optimization algorithms, there's been several new ones that have come out. I think recently I saw one come out of Berkeley that uses radial basis functions to perform those optimizations. And I again went into Python, put together a software plugin for that to bring that over into my EM modeling setup, and it performs exceptionally well. You can get away very often with 15 or 20 iterations as opposed to several hundred possibly with other algorithms. So mathematicians, computer scientists, and engineers, there's a lot of development effort into those optimization algorithms because they are critical. The days of going and manually tweaking and tuning things, not that it's come to an end at all, it still does happen with the prototypes, but for the most part with filters like what you're seeing over here on the right, the design's well known. We know exactly what we need to adjust, and it's relatively simple. But parameterizing the entire design allows you to come in here and adjust things like your line width, which is going to affect center frequency. It affects your gap width in here, which is going to impact bandwidth. So you can come in here, you can move this up or down, your input and output lines, which are going to have an effect. Capacitive stubs out here on the end, via radius and cap diameter out here. A lot of these things are critical, and it's a large number of variables, which is where those optimization algorithms come in. There is some level of intuition that comes with having designed these filters with, for a while, and understanding that, okay, if I adjust parameter A, this is what's going to happen to the response, and that's helpful to eliminate some of those variables, but we can't do it entirely. So again, the novel applications, we're definitely getting a more hands-on approach with that. We don't have templates designed for these. We don't always have an idea of what adjustments to parameters are going to do to the filter response immediately. And very often that comes with time, and that's where a lot of those lumped element models do come in handy, is I can, extend the line out and adjust the capacitance, adjust the inductance. Hopefully that will maintain the same impedance, ideally, but I can adjust these things and be able to see very quickly what impact it might have on the response, even if it's a very rough idea. Very often we'll get requests for custom rejection. Harmonics is going to be a big one, not just amplifier output harmonics, but those harmonics that are in a reentrant phenomenon that are actually generated by the filters themselves. So again, just as a rough idea here, if I'm looking at my frequency down here on the bottom and my magnitude over here, a low pass filter, typically they'll illustrate it as, something like this. In reality, you get this clean roll off, and then there's right here, you'll typically get some form of a reentrant phenomena that comes up, and this will happen with band pass filters. This will happen with most filter topologies. So what we're typically asked to do is, hey, can you minimize this as much as possible? And that's going to complicate the filter architecture because that goes against the basic operation of the filter. So there's very often a need to add additional structures in order to help to attenuate that portion of the filter and get a nice, relatively clean stop band out here, which in reality, looks more like this. But they're happy with it, and that's all that matters to us. Real estate limitations, another big one. Customers are consistently trying to reduce component size because they're getting very limited on their PCB size. So, can you make the component as small as possible? That's what I very often hear, as small as possible. And they may not even have requirements for the exact size, but it's, hey, this is too big. Can you make something smaller? Cost constraints, that comes into the thick film technology, which I'm going to cover. Surface mount requirements. All of our devices, for the most part, are going to be surface mount, which is one of the big reasons that customers come to us. Wire bond is not necessarily easy with high frequency, but it's a little bit more complicated, and of course, fragility issues that come along with that. And that's not to say that the surface mount transitions are perfect by any means. They do have their share of issues, but it simplifies process for our CMs, our contract manufacturers, that actually mount these devices for us. Lead times, PCB design impact, I kind of covered that already, where our customers not only want the device, but they want to know exactly what impact this is going to have on the PCB itself, and vice versa. We may want to know what effect a PCB structure underneath the device is going to have on the filter itself, on the bridge or isolator or whatever it may be. And that's where we will elect, before the customer even does, to begin developing those PCB device component models, because then what we can do is we can go back to our filter design, add some capacitive compensatory structures, or reduce the line width right at the input or output to help to increase the inductance if we do that. So there's some reasons for doing that. Real estate limitations, and I brought this up, how do we fit a traditional 5 gigahertz microstrip filter onto a 5x5 substrate? The quick answer is, for a traditional topology, we don't. And this is one of those more novel applications that we have to begin stepping into in order to accommodate that requirement for our customers. So there's been a lot of advances in resin structures, and when I say advances, a lot of this has been even the last 20 years. So I've noticed very often what will happen is these academic papers will be pushed out, and not just academic, but industry as well. They'll show up in an IEEE journal or some other, relatively popular publication, and they just kind of get buried for a little while. Maybe nobody notices them, or they're just randomly picked up at some point in the future, and somebody decides to go running forward with it. So the complementary split ring resonators are a great example of that, where you're not actually creating a conductive ring itself, but you're creating a conductive plane and then etching a ring out of it. Those have been around likely for decades, but you're starting to see them a lot more frequently, especially with things like the substrate integrated waveguides. One of the things I've noticed in some of the relatively recent academic journals is, if we look at the top conductive layer for our SIW, and then you'll have your transitions here and here, what I've been seeing more frequently is a set of coupled complementary split ring resonators to actually develop the filtering mechanism for these filters. And it's kind of an interesting application, because typically with the SIWs, usually your filtering mechanism will be very similar to what you see with a rectangular waveguide. And that's typically going to be an iris-based design, which I believe I've got a photo of, but just in case. So if I'm looking down the end of the waveguide, your iris-based design is going to basically clip off a portion of this, such that, if I look at it longitudinally here, my poor drawing ability, but so I went into engineering. I'm not an artist. There we go. Maybe. There we go. Okay. So yeah, if you're looking at this lengthwise in the waveguide, you'll usually have some form of rectangular structure here that's going to change the reactance in that portion of the waveguide. And each one of these forms a different pole on the filter, such that an incident wave here is going to be affected by these various irises in here. And another method of doing that is just a big inductive post that's stuck down all the way through the waveguide. And you'll see this as well. But everything that we've applied here is also applicable to the substrate integrated waveguide here. So a lot of the mechanisms are almost identical. So for the SIW, as opposed to those rectangular iris-based windows, we'll usually use like a set of discrete vias. And this, of course, will be symmetrical. So it'll look something like this, usually with the discrete vias. And you'll notice this is very common in a lot of the papers that you see for SIW is a mechanism like this, and then this will stretch over to this side, so it's symmetric. And same concept, I can remove these vias and I can put large inductive posts in here, which ultimately are going to end up being vias. But I typically don't like that topology. And the reason for that is that via diameter for the thick film process especially is a lot tougher to control. And here that via diameter for these inductive posts is critical. So I typically will try to avoid that design, even though I have set the software up to be able to do that if we need to at some point in the future. But beyond that, for the device architectures, fractal patterns have been around forever. We've all seen those. The quintessential cell phone antenna is going to be a big one. Defective ground plane structures, which are really cool. That's something that I need to play around with a little bit more. And then your typical stub-loaded resonators, which is going to be something like this here. And multi-layer architectures, which is going to be another big one. So as opposed to just having a single planar filtering mechanism, they may epoxy substrates together and create several different conductive layers stacked on each other, and then introduce the filtering in a full 3 dimensions to be able to get the specific filter characteristics that they're looking for. So as I said, vast majority of our single layer thick film devices are microstrip CPW based, coplanar waveguide. Both of these are going to come with their share of problems in mmWave, and they give me an absolute headache. Especially with the microstrip, it's primarily with the microstrip. The substrate thickness that you're using is going to be inversely proportional to frequency. So the recommendations I've seen for an alumina substrate, which is one of the most common ones for both thick and thin film, is 25 mil, typically up to about 20 gigahertz, 15 mil up to about 40 gigahertz, and then 10 mil up to maybe 70 or 80 gigahertz. Through a lot of simulation work that we've done, we found that we're able to push these actually well beyond that without running into a lot of those issues that you do see with that higher substrate thickness and higher frequency with an equivalent microstrip size. Multimoding becomes problematic with these at higher frequency. It usually takes a much higher frequency for it to become extremely problematic. Generally, the substrate becomes an issue prior to that. Of course, you've got increase in metal, dielectric, radiative, and surface roughness losses. Surface roughness was something that for the longest time, nobody really paid any attention to, because down at 5 gigahertz, you don't even notice it. When you start getting up into maybe 70 or 80 gigahertz, it becomes a huge, huge factor in the overall loss of the device. Variable effective permittivity. And this was something that I thought was actually pretty interesting, because this is not something that is stressed on very often either. So the equations governing your microstrip impedance, if you look at a lot of those, they're going to be based on permittivity, they're going to be based on line width, substrate height. Those are the 3 big variables, but very few of them actually bring in frequency. And again, the reason for that is down at 5-10 gigahertz, there was no real difference in line width to achieve the same impedance. At those frequencies, it might be 49.8 ohms versus 50.0. There's not enough of a difference for it to be concerning. But what happens is, so if you look at this image over here on the left, this is a simulation looking down this portion of the microstrip. So we're looking this way, and we're looking at the electric field pattern of that microstrip in operation. So over here on the left, we have this at 1 gig, and on the right at 80, which is relatively close to what we're seeing for a lot of the 5G frequencies now, which I think go up to, it's in another slide, maybe 72 gigahertz. But what's happening here is, if you notice with the 1 gig microstrip line over here on the left, there's a lot of field sprawl coming out. So there's a good portion of the field that's actually concentrated down here where it's supposed to be with the microstrip, but you end up with a lot of sprawl in order for this to achieve that return path down to ground that we're looking for. And so, as we know, there's an effective permittivity that's associated with that because the fields spend a portion of their time up here in air. Not sigma, epsilon. I told you it's 3 in the morning. You can't blame me. So it spends a good portion of its time up here in air, where you end up with a relative permittivity of 1, and a good portion of its time down here, where your permittivity is equal to roughly about 9.4 in alumina. 9.4 to 9.6. But what happens is you end up with an effective permittivity for the microstrip of, something around 6 to 6.5 maybe at this frequency. But up here, what you'll notice is you end up with that same electric field concentration that's primarily going almost directly straight to ground, but your field concentration up here is a lot tighter. And one of the things with microstrip is that as you start to approach an infinite frequency, ideally these electric field lines are going to be completely vertical in this manner here. Of course, infinite frequency is not a thing, but the idea is that as you step up in higher frequency, this stray field that's coming off here to make contact with ground is starting to come in a lot tighter. And so what happens if I'm designing for a 10 mil thickness substrate, my line width at 5 gigahertz, for example, might be something along the lines of, 9.8 mils. Let me get my hand on here so I can actually write. So 9.8 mils at 1 gig. Up here at 80 gigahertz, that line width, and this is kind of counterintuitive, the line width will actually increase, not decrease. So you would expect a need for a higher impedance, but you're actually reducing it in order to accommodate that. So at 80 gigahertz, your line width might be something around 13 to 14 mils. And that's a big jump. So if we were looking at 9.8 versus 9.9 to achieve the same 50 ohm impedance, that's not a big deal. It's something you can completely ignore. But when you start stepping up into a line width like this compared to this, that's going to be a big difference in your line impedance, and that's going to affect the overall performance of the device. So this is something critical that we've started taking into account. And software now, so ADS, the line width calculator, will actually take this into account. And that's one of the reasons they ask you specifically for your design frequency. Very often what I've noticed, people, students, especially, and some engineers, they just leave it sitting at 1 gig. They're like, oh, this doesn't matter. I don't need to touch this. I just need an idea of my line impedance. I don't care about electrical length. Well, no, you probably should. You're designing a component at 70 gigahertz. You should, accommodate for that and look at your line width difference there. So getting into SIW a little bit, one of the key benefits is this is resistant to a lot of the effects of the high frequency application in microstrip. One of the most beautiful things of this is that it is relatively impervious to substrate thickness, and that is a key. And when I say impervious, you're not looking at massive changes in the center frequency. You're not looking at major changes in the response. What you will see as you increase the thickness is a slight jump in return loss, but it's nothing significant. So where we may have previously needed a 10 mil substrate in order to achieve 60 gigahertz, for example, we'd need a 10 mil substrate to achieve that with microstrip. With the SIW, we might be able to get away with using 15 or potentially even 25 mils. A lot of the issue, and I'll get into this with the disadvantages though, is the transition. SIW transitions for the most part have been microstrip and CPW based. Which is problematic because if we start stepping up to 60 gigahertz, we run into a lot of the same issues with that microstrip that we did previously, albeit with a shorter line length, which is going to help to reduce some of that. Conductor radiative losses are reduced. You still end up with dielectric losses that are going to increase with frequency, and surface roughness is still problematic with the SIWs. The permittivity is going to remain more constant. As I said, the effective permittivity here is not as much of an issue, if an issue at all. Return loss looks great at high frequency, and they're relatively easy to design. Once you get that initial idea of design laid out, they're relatively simple to actually get into modeling and get built. So it's kind of the point where I can get one of these typically from a rough idea of specification out to a full-blown, this product is ready to manufacture within 2 to 4 weeks, which is relatively quick. And of course, very tight EM field control, which is a big one. These are basically, if you think about it, because of that sandwiching property of those two vias and that top and bottom plane, a waveguide, it's a field sandwich. Because of that, there's a lot better field control. You don't end up with as much radiative loss coming out of it. You don't end up with a substantial amount of leakage, with the exception, again, down here. If you look on the edges of this is where most of your leakage is coming from, is right around that microstrip and that taper. For the most part, you don't see a substantial amount on these vias. And I'm not sure what frequency this operates at, but it's not too terrible at lower frequency. Big disadvantage, the structures are quite a bit larger than would normally be required by microstrip at the same frequency. So I will typically tell our customers, don't design an SIW, down at 5 or 10 gigahertz. You're going to have a massive device that is not going to really provide you much benefit at all. And there are some exceptions to that. Cavity resonators is an example. SIW technology is great for those, even at lower frequency. So as I said, they're still utilizing the same transitions, which is problematic. This is another big one. They are more sensitive to permittivity variation in the substrate. And what I mean with that is, seems like it's a contrasting idea from what I said previously, but there's a different reason for this. So there's going to be some tolerance involved with your substrate permittivity. They will tell you it's 9.4, but in reality, it might be 9.3 to 9.5. In a microstrip, because you have that concept of relative permittivity, or not relative, but effective permittivity, it's less of an issue that the substrate's slightly lower because you're spending a portion of that time in a different permittivity. There is less of a lower percentage decrease or increase in the permittivity using microstrip, that effective permittivity, versus the substrate integrated waveguide where the entire field is sitting inside of that substrate. So if my permittivity is 9.3 versus a specified 9.6, that's going to cause some performance issues. Manufacturing, of course, is going to be a little bit more complex with that, and that's primarily due to the vias. Especially at high frequency, it's a normal consequence that the diameter and the pitch of these vias is going to have to be reduced. Other than that, there is actually some benefit that I didn't mention, and a lot of that comes down to line width and fine line. Because this is basically just a big, simple conductor sandwich, there's not a lot of need, or any need in many cases, for any kind of tight line width control or tight gap spacing, which is going to be another big one. So we're not having to create these very tight, 25 micron gaps in between transmission lines, which is a big advantage of this. So I kind of got into this a little bit, but two of the big applications for the SIWs, high-pass filtering, and that's due to the natural characteristics of a waveguide, in that you're going to have a lower cutoff frequency below which the waveguide's not going to operate, and you're going to have an operational frequency, and then you're going to have some form of an upper cutoff where waveguide begins the non-dominant modes. So they kind of lend themselves to being natural high-pass filters, which means that we can just go and introduce a few more poles into it and create a beautiful high-pass filter out of that. Bandpass filter designs, as I discussed, this is a very, very common topology for this. These are designed using set J inverters. So looking at various capacitances inducted in these cavities and these windows here that are formed by the vias. So you're mainly looking at these windows and the distance between them. And those are going to be your two governing parameters to actually adjust the characteristics of those cavities and adjust the pole location of your filter. These can also be implemented into resonant cavities for very high Q applications, which is very critical for 5G. Bandwidth has done nothing but get smaller, surprisingly. Film, still tried and true method, even at millimeter waves. There's been, I don't want to say a movement or a push to basically say that film it's relinquished to lower frequency. It's not effective at millimeter wave, and that's actually not the case at all. It is very cost effective. It's a very timely means of fabrication. I can push from prototype to manufacture extremely quickly. High degree of customization. I can do pretty much anything the customer wants, make changes very quickly with this. The initial engineering costs, relatively low. Of course, there are some downsides, surface roughness being a big one, transitions coming off the substrate being another one, because we're typically not using wire bonding, even though we are able to. Alumina is still a big one for both thick and thin film. They're popular for very low loss, excellent mechanical strength, polish, You can get these polished. Of course, that might introduce some issues with thick film. And yeah, in addition to that, the high permittivity is also a big point of love for alumina, and that's going to be due to the feature size, due to the changing wavelength of a particular field going into that substrate, which reduces the element size required. So some of the evolution that we've seen in thick film, number one, fine line processing, which so it's kind of a combination between the screen printing process and the photolithographic process of thin film. And what we're able to do is actually reduce those line widths of the thick film components down significantly. So you can see down in here, this is one of our modules for our oscilloscopes. You can actually see the line width down here, and this is all performed on thick film. There is no thin film portion to this. But we've been able to stack up several layers, integrate ICs, die into this, create our own dielectric on top of it, develop our own transitions. There's quite a bit that we can still do with thick film. That transition technology is constantly evolving. So right now, typically, microstrip, CPW, those are the two big ones. But we are evolving from there. There's a lot of work that you'll see again in IEEE's journals on trying to improve those transitions. And new materials and paste, of course, they're always a continuing area of research. Thin film, nearly identical design process, slightly different manufacturing process. And what I wanted to show here, number one, you end up with a lot of similar substrates. Sapphire, as we know, is still in a different crystal form. But this has extremely low loss, even lower than alumina, and it's relatively inexpensive. So this is going to be one of the big ones, in addition to fused silica for thin film. But what I wanted to show over here on the left, this is the module out of Keysight's 110 gigahertz oscilloscope. And if anybody's interested, this is actually a really cool video. There's a third party that actually takes one of these apart and goes in and discusses the theory of operation of this, which is really interesting. It was actually officially sponsored by the company. Gave them the board and said, here, tear this apart and give us a nice video. It was really cool. But basically what I wanted to show with this is the integration of a thick film component, and this is extremely large. This is not typical. So integration of thick film, and then down in here you have thin film components. So this one you can see is surface mounted to the PCB in 5 different locations. This is a modified Wilkinson splitter. And then down here you have your thin film component. This is going to be wire bonded out to the traces as needed. So there is some hybrid mechanisms involved that we very often use. So just real quick, looking to the future, 5G, of course, is going to continue to be the big one. Oh, so close. I said 71 gigahertz. So they're saying this is going to make up roughly about 25% of the mobile technology market here in just a couple of years. It's large. It's a very active focus. I would say for the most part, if you look at companies like Motorola, Qualcomm, my company, Tektronix, if you go even to their website, you'll see there is a ton of marketing and material out there for 5G. We do 5G where we're consistently evolving in 5G. Look at everything new we're doing in 5G. So it's a very big one right now. 6G it's effectively in its infancy. It's almost still sitting in a lab at this point. They anticipate that it's going to push into the sub-terahertz realm, which is going to be on the high end of millimeter wave in some applications, up around 300 gigahertz. But there are some that are stepping up, apparently to 600 or 700 gigahertz. China most recently launched a satellite and actually proved some of that sub-terahertz communication with the satellite, which was really, really interesting. And they're looking to start pushing this technology out around 2030. So there's quite a bit of time before we start seeing that. And there's currently no agreement on standards. So at this point, industry is pretty much just predicting what's going to happen. Quantum computing, another big application. You look at that and you're like, okay, this isn't millimeter wave at all. Well, it is the case with a very basic structure of the quantum computer, but there's a lot of RF systems behind that quantum computing setup to provide control and data feed through from this setup. So we have actually developed some devices for Keysight's quantum computing division. So they have asked for several filters for this. And these are looking to have a significant amount of growth as well. So there is going to be some application for millimeter wave to this particular market. And it's increasing 43% in between 2020 and 2030 projected, and going up to $9 billion US from 260 million. So there's a big jump in the market, and that is an active area of research and R&D investment. And then I think this is the final one. Ongoing applications. So extremely high frequency EHF line of sight communications, satellite constellations, especially for defense applications, Milstar and the advanced EHF satellite system. Security scanners, as we're all painfully aware of. Usually we end up having to go through them, and then medicine is another application. And there's a handful that are emerging, and this is either happening now or in the very near future. One of them is the new wireless standard. Automotive, always a growing market, and this again is one of those ones where you just see a plethora of marketing material. Device interconnects and large networks such as data centers, these are two big ones as well, primarily for number one, speed, and number two down here with the data centers is heat management. So I think I pushed right up to an hour, but I'll open it up if anybody has any questions. The chat probably is the best place to put them. That is a lot of material. I did generate 3 of those MCQ questions for you. I put them into the slides. I don't know if you actually still need those from me or not, but they are available for you.
Sorry, Mr. Madsen, actually my connection was lost, so I didn't get in a couple of minutes.
Oh, no, that's okay. Yeah, I saw you dropping in and out a little bit, but
actually there is some issues with my internet connection.
Oh dear.
Okay, so I hope your presentation is completed.
Yes, yeah, that is the conclusion of it.
Yeah.
As I said, if you need those multiple choice questions, I have them available. I put them into the slides, but if you need them for anything, I can send those to you after the
okay.
meeting.
No issue. And thank you for your presentations regarding that the technological perspectives that you have shared. That is, you are experiencing actually. That we are actually academically knowledgeable, but don't do such of kind of things, that challenges we are not facing in real life, that you face
Right.
whenever you are designing some components for any to deliver some company or some other persons. Okay.
Absolutely. Yeah, there's always that big separation between academia and industry.
Yeah.
And I feel like you guys feed more to us than we feed back to you. It's kind of an unfair relationship. So I mean, a lot of this work is coming from the universities. I mean, even the algorithms, for example, the simulation algorithms, a lot of these are not coming out of industry. So yeah, thank you. I don't think anybody ever tells you that.
Yeah. Thank you for your valuable time and for accepting our invitation to deliver such wonderful talks
Absolutely.
in this program. So we'll look for in near future. You must will be with us for different kind of research related activities, so that we can enrich our knowledge and we can go ahead together.
Absolutely. I'm always available if you need anything.
Yeah. Thank you. Any participants have any questions? You can raise your hand. I will unmute it.
Yeah, passive devices aren't exactly on the cutting edge for millimeter waves. So
yeah. So I do actually researching on antenna, and I use HFSS to design in practical HFSS for designing that microstrip antennas.
Oh yeah, absolutely.
Okay, so I work on that field actually.
Okay, yeah, fantastic.
Okay,
Now that's something they've actually been asking us about recently is, hey, can we do antennas? Nobody's specifically come to us and asked for one, but yeah, it was a conversation I had oh goodness, it feels like it was a couple of years ago, asking if we could do those. And I said yes, and then never heard anything about it. So maybe at some point I'll be designing those. But yeah, HFSS that's a fantastic piece of software. It really is.
You have mentioned on alumina that is over the substrate, a layer of alumina. So a layer of alumina over substrate. So that is actually you are using to design the microstrip line.
Correct.
Okay. So whether that is much costlier than copper, or what are the advantages, disadvantages with respect to the copper layer over the substrate or alumina layer over the substrate?
Are you talking about like the contrast between, say, for example, PCB versus thick film and using the alumina? So primarily, you can very often, and I have seen that people integrate components directly into PCB. So you'll see things like hairpin filters that are integrated directly into that copper trace, and there is a lot of benefit to doing that. I am curious what frequency that's actually gone up to. I don't know. And I also don't know with PCB what level of line width control they actually have over the copper. That's one of, I know the big reasons that our customers come to us is with the higher frequency and the very special applications is getting that very tight line width control, very tight gap spacing. And then having it available as a component that they can, something needs to be modified. For example, they can remove that component. We can go back and create a revision of that. Say they need to increase the frequency a little bit, maybe it's not working with their system. They can just pull that component out, get rid of that part number entirely, and we'll generate something completely new for them without having to go in and adjust the PCB at all. For the most part, these components, they are surface mount cookie cutter, meaning we don't need to make any adjustments based on the underlying PCB. Usually, there are exceptions to that, and that's where we come up with those compensatory structures. But it eases the ability to pull a component off, put a component on, and change things as needed. That's probably the biggest benefit I can think of. But I would be curious to know what the bandwidth control is on PCB copper.
Okay. Thank you very much for your nice presentations, and we have also have get some knowledge from your presentations, and actually the presentation we have recorded, and for future we must just going through this.
Okay.
Okay. Thank you very much, and have a great day.
You as well. Thank you.
Yeah. Okay. So with this presentations by Mr. Madsen, we are actually completing our lecture sessions of this 5-day FDP on the recent trends in microwave and millimeter wave communications.